Thank you so much. Sorry for the delay. My name is Landon Hamilton. I'm from the University of Colorado Boulder and Dr. Noka's Neurophysiology of Movement Lab. The talk I'll be giving today is entitled Motor Unit Characteristics and Walking Performance in Persons with Multiple Sclerosis. Multiple sclerosis is a debilitating neurological disorder that impairs mobility, decreases daily physical activity, and reduces quality of life. It's the most common cause of non-traumatic disability in young and middle-aged adults. Onset typically occurs between 20 and 40 years, and walking performance is often used to quantify disease status. To address these issues with walking performance, we created and performed an intervention study that we've submitted and is currently in review for publication entitled Neuromuscular Electrical Stimulation Improves Walking Performance, Neuromuscular Function, and Disability Status in People with Multiple Sclerosis, Double-Blind Randomized Trial. The purpose of this study was to compare the effects of a 6-week intervention using neuromuscular electrical stimulation on walking performance, neuromuscular function, and disability status of persons with relapsing remitting MS. The outcomes were that we improved walking performance, increased lower leg strength, improved plantar flexion force steadiness, and decreased self-reported measures of fatigue and walking limitations. So what's new and noteworthy in regards to this intervention was that it's the first intervention to measure lower leg muscle activity with high-density EMG in the MS patient population. It's provided non-invasive motor unit data for an understudied cohort, measured muscle activity from separate muscles during the same action. And so using these secondary variables, we also submitted an additional publication entitled Motor Unit Discharge Characteristics and Walking Performance of Individuals with Multiple Sclerosis, and this is more of what I'll be speaking about today. And the purpose of this study was to examine the associations between force steadiness and motor unit discharge characteristics of lower leg muscles with clinical assessments of walking performance and disability status in individuals who self-reported walking difficulties due to MS. Data was recorded at weeks 0, 7, and 11 during the intervention and were treated as independent outcomes used to predict walking performance. So we have the initial screening period where we identified individuals for the study, performed the initial evaluation, had 6 weeks of intervention 3 times a week, then had the 7th week of evaluation after the intervention, allowed 4 weeks of recovery, and then had the final evaluation. On day 1, we assessed walking performance with the 25-foot walk test. So it was a measure of walking speed, so how quickly or how much time it would take to walk 25 feet. 6-minute walk test as a measure of walking endurance, so how far they could walk in 6 minutes. Manual dexterity was assessed with the 25-hole grooved pegboard test. And disability status was assessed with the patient-determined disease steps, modified fatigue impact scale, and MS walking scale 12, which were all self-determined assessments. On day 2, we measured muscle strength with MVC torques in the supine position, measuring plantar flexion and dorsiflexion, force steadiness for the less affected limb, so they were determined themselves which leg was less affected, at 10 and 20% MVC torques and plantar and dorsiflexion, and also performed high-density surface EMG with the Listen WEMG system. And this was the first prototype developed by Listen with the specific purpose of detecting high-density EMG in dynamic conditions. So as you can see in panel A, I'll sort of go over the point. We have the placement in the top left for the medial gastrocnemius and the soleus. B, we see the tibialis anterior. In panel C, we have our 4x8 electrode with the bipolar EMG recording for a 30 millisecond window. And then additionally, we have in panel D our example force trace, where we use the analysis window of the steadiest 30 seconds. Motor unit discharge characteristics were identified with the decomposition algorithm for HDMG based on Olibar et al. 2010 and the Olibar and Zazula 2007 papers. In addition to that, once we identified motor units, we included additional exclusion criteria based on single motor unit recordings from previous studies. So the initial inclusion criteria included interspike intervals less than 25 milliseconds or greater than 400 milliseconds, coefficient of variation for interspike interval less than 8% or greater than 55%, interspike interval distribution skewness in a range of negative 0.5 to positive 0.5, and coefficient for variation of interspike interval less than 10% and a distribution skewness of less than 1. So with the results, we had 23 participants. Average age was 53 years. We identified 3,232 motor units across 65 experimental sessions with 488 successful EMG trials, approximately identifying 5 to 7 motor units per trial. For the tibialis anterior, we identified specifically 1,634 motor units, with the mean interspike interval being 110 milliseconds for the 10% force target, and then 20% at the, we had 102 milliseconds. Comparing 20% to 10%, the interspike interval was statistically briefer. For the gastrocnemius, we identified 696 motor units, at the 10% target being 138 milliseconds, 135 for the 20% MVC torque. There was no statistical difference between the 20% and 10% target in this category, but comparing gastrocnemius to the tibialis anterior, there was a statistical difference from comparing both 10 and 20% respectively. And for the soleus, we identified 902 motor units, with 150 milliseconds being the mean interspike interval at 10% and 145 milliseconds at the 20% target. For the 20% compared to 10%, it was again statistically briefer for the soleus, and comparing the soleus to the gastrocnemius, it was statistically different, and additionally comparing soleus to tibialis anterior, statistically different as well. We used a linear regression model to predict 6-minute distance, and we were able to explain 40% of the variance with 2 predictor variables. The first predictor variable being mean interspike interval of gastrocnemius at 10% MVC with a negative partial correlation, which indicated that individuals with briefer mean interspike intervals walked longer distances. And the second predictor variable being MVC dorsiflexor torque of the more affected limb, having a positive correlation or partial correlation, which indicated that individuals who were stronger walked farther. In our 25-foot time regression model, we were able to explain 47% of the variance with 3 predictive variables. The first being mean interspike interval of the soleus during 10% MVC. This is a partial or positive correlation, so indicating that those who had greater or a longer interspike interval took longer to walk the 25 feet, and conversely, those who had briefer interspike intervals walked faster. The second being MVC dorsiflexor torque, again, of the more affected limb, with a negative partial correlation, indicating again that those with less strength took longer to walk 25 feet. And lastly, 20% of MVC force steadiness of plantar flexors with a positive partial correlation indicated that those who were steadier around the 20% force target were able to walk faster, and again, conversely, those who were less steady took longer to walk that 25 feet. So in conclusion, moderate amounts of the variance in 2 tests of walking performance for persons with MS were explained by the neuromuscular characteristics of lower leg muscles. I'd like to thank everybody in our lab, the neurophysiology of movement, particularly Awadam Lukalis, who's the first author on the paper, Leah Davis, and Dr. Roger Anoka. Funding was provided by the Eunice Kennedy Shriver National Institute of Child and Health Development of the NIH. I'd like to thank the Listen Lab, particularly Alberto and Tyann, for implementing the WMG and helping us with that system. And particularly OT Bioelectronica, thank you for having me here today to be able to share our science and research with you guys, as particularly Andrea, Enrico, and Eugenio, letting us and helping us use the new Sesente Quattro device and moving forward with that type of research as well. Also, Dr. Noka wanted me to point out that next year, from 11th to 14th of July 2018, there's the International Motor Neuron Society meeting on CU Boulder's campus. So if you'd like, here's the website, motoneuron2018.org, for more information, and we'd love to see everybody there. Thank you so much.